let's look at some examples where we can calculate the distance traveled and compare that to the displacement of an object. If you recall, when we talk about distance, we're talking about the total path traveled. We call this a scalar quantity, meaning there's no direction, it's just the size or the magnitude, whereas a displacement is defined as a change in position. So I can actually change my position and there's a direction component. And I actually don't care about the path. So a good little description would be this little image here. We got this bug moving along. The blue curved line is the distance. If you are measuring with your car's mileage or your odometer, that mileage would capture all of that blue line. However, the displacement at any given time would be the direct line path, the red arrow, to that bug's position. The total displacement would be an arrow from point A to point B. But as that bug moves along, the displacement is to the right, then it's to the left. It's changing as it goes. One common way that displacement is referred to is as the crow flies. If this was a bug and it wanted to get from point A to point B, it doesn't have to crawl on the ground and follow a path, right? It can go directly from point A to point B if it flies there, right? So there's a common phrase, as the crow flies. I want you to think displacement when you're doing that. So let's look at a quick example here where we're going to add values. Let's say we move 5 meters east, then 3 meters west. All right, just a simple two motions are happening, and it's always helpful if we draw a picture. All right, so let's mark where we started. We started right here. I like to put an I for initial, and we're going to move 5 meters east. So I'm going to draw a little arrow. All right, there's 5 meters, and my arrow points to the right. That is what we would call a displacement. All right, there's an amount, 5 meters, and a direction to the right. From there, we would then turn around and go back 3 meters. So this is 3 meters. And we would finish right here. Now, obviously those lines would be right on top of each other, but visually I wanted to make sure you can see the difference. Now notice, 3 meters west would be an arrow that points left on my page. That is another displacement value. So if I want to know the total distance, distance doesn't care about direction. The total mileage I would have, the amount of distance I traveled, would just be the 5 meters plus the 3 meters. I would have traveled 8 total meters of distance. However, my displacement is different. Displacement is our change in position. It is delta x. All right, so if, let's say I started right here, my x initial would be a position of 0 meters. Well, where would I finish? Well, my x final would be, if I went right 5 and then left 3, I would be at positive 2 meters. Right? And so I can actually add those two displacements together to get my total displacement, or my delta x. But delta x would be x final minus x initial. Those are where I'm located. Well, at the end, I'm located at positive 2 meters. At the beginning, I'm located, let's call that 0. And so I would be displaced 2 meters, and it would be a positive displacement, which would indicate that I'm displaced to the right by 2 meters. Now, it turns out visually, we can do this as well. If you notice, from my initial position to my final position, I could draw one arrow to get there, and that arrow would have to be 2 meters. That would be my total displacement for that trip. Once again, my distance would be the dotted line, that full path. My displacement would simply be that little bit, right? So I can add them together and do that. And it turns out, mathematically, the blue arrow, my 5 meter arrow, if I add that to my 3 meter arrow to the left, I draw the arrow a little shorter, I can mathematically write them as numbers. 5 meters to the right, I'm going to call positive 5. And 3 meters to the left, I can call -3. And when I add +5 and -3, I get +2 meters of total displacement. Okay, so we have a lot of different ways to look at this. I think drawing a picture and showing it graphically, as I did here, gives you a really good sense of what that displacement would be. Now, I can move up and down, and the same thing would come into play. Now, what gets a little tricky is when we start having things move not just horizontally, left and right, or not just vertically, up and down, but what if something moves to the right and up? What if I travel 5 meters, I'll do this in blue again, 5 meters east, then, sorry, let's change this value here. We'll make it a little easier here. We'll call this 3 meters east and 4 meters north. All right, well, let's draw a picture of what that's going to look like. So I would be starting right here. I'm going to call that my initial position. 3 meters to the east would be an arrow that starts here, and let's call that length 3 meters. And it points to the right, which is to the east. From there, I would then move 4 meters to the north. So there's 3 meters. Let's go a little further. We're at about 4 meters. All right, to the north. So again, the arrows are my displacement vector quantities that show me my path, which means I finished right here. Now my distance that I would have traveled would just be the total path. 3 meters plus 4 meters would be 7 meters of total distance. But my displacement is a little bit different. My displacement is my change in position. Well, how's my position changed? Well, I've gone from my initial position directly to my final position. That length is my displacement. What is that length going to be? Right? So mathematically or graphically, I can actually calculate this. You might have learned in geometry about right triangles. A right triangle has a 90-degree angle right here, and you have 2 legs, and sometimes you'll label the legs, leg A, leg B, and the hypotenuse we call C. And there's something we call the Pythagorean theorem. The Pythagorean theorem allows us to calculate the length of the hypotenuse, the long side, C, if I know both legs. And Pythagorean theorem says that if I take one leg squared plus the other leg squared, I would get my hypotenuse squared. And so if I can find the length of that black arrow, then I know my displacement, the straight line path from start to finish. And so I can actually plug in my values. I would have 3 meters squared plus 4 meters squared, and that has to equal my hypotenuse squared, which would be my displacement. Well, that becomes 9 meters squared plus 16 meters squared, and that is C squared. And look at meter squared and meter squared, I can add those together. They are like terms, which gives me 25 meters squared is equal to C squared. And to solve for something that's squared, we can take the square root of both sides. And look what our units end up working out nicely. Meters squared, the square root of that is meters. I end up with 5 meters is what C is. And it turns out 5 meters would be my displacement. So we can use Pythagorean theorem to figure out what the displacement is if I know the legs of that triangle. So let's take it one step further. What if we go down 4 to the right 6, I'll draw that about a little longer, and then we go up 8. what is my displacement? Well, my distance would just be 4 meters plus 6 meters plus 8 meters. It would be 18 total meters of distance. But my displacement, I would start here and I would finish here. And I would go in a straight line path from here to here. Well, overall, it looks like I would be traveling to the right 6 meters, and I would be traveling up 8 minus 4 is 4 meters. So I have the two sides of my triangle, and I want to know what is that. So to calculate my displacement, I would say, well, 6 squared plus 4 squared are my two legs, has to equal the hypotenuse c squared. Well, 6 squared is 36, plus 4 squared is 16, equals to c squared. That's 52 is equal to c squared, and that's probably where I need to pull out my calculator. And I can find that the square root of 52 is 7.21. So my displacement is 7.21 meters, which makes sense, right? I've gone 7.21 meters from start to finish. All right, so we can add up all these different motions and determine our total displacement using Pythagorean theorem. Now, the last example I want to show you is when we maybe go in a circular path. So what if I start here and I'm following a circular path and I finish right here? Well, what is my distance? Well, I would need to know something about that path. And it turns out that is a circular path, and I might know a radius, right? The radius, let's call that 2 meters. Well, this is called the circumference, would be my total distance. And the circumference of a circle is 2 pi times the radius. So in this case, this would be 2 times pi times 2 meters. So 4 pi meters, and 4 times pi, 4 second pi, gives me 12.57 meters of total distance. Now, it turns out another equation for circumference, well, my total diameter, that would be a diameter, d. Just twice the radius would be 4 meters. Turns out circumference is also pi times d would be this circumference, which it turns out pi times 4 is what we got this to be equal to as well. So I get it two ways. Now, what's my displacement? Well, hopefully you recognize that for the total motion, I started where I finished. X initial is equal to X final, and so my change in position is going to be 0 meters. There is no displacement when I take a circular path. Now, what if I did a halfway path? What if my final position, what if I started here and I went half the circle and I finished here? Well, I would need to know my radius. Let's say R is 3 meters. Well, the total circumference all the way around would be 2 pi times the radius, but I'm only going halfway. So 1/2 of the circumference would be 2 pi over R over 2. And so I can just take pi times the radius, and I would get 3 times pi, and I would get 9.42 meters would be my distance. And my displacement would be the straight line path from initial to final. Delta x would just be 2 times the radius. It would be my diameter.